Welcome back to the Deep Dive. We're here to break down complex tech research and give you the insights you need fast. So, you've probably heard a lot about Rust. It seems like it's topping every developer satisfaction survey out there. But satisfaction, that's not quite the same thing as productivity, is it?
That's really the core question, isn't it? Is Rust, genuinely the future for systems programming? Or does that initial cost, the learning curve, mean it's only practical for, let's say, specific niche projects?
Right.
So, to figure that out, we're trying to cut through some of the hype today. We're looking at a really pragmatic set of sources, detailed notes, project experiences from a veteran systems researcher.
And this is important. This isn't someone new to programming. Our source is a C++ expert, deep background in algorithms, EDA, electronic design automation.
Yeah, exactly. Fields where performance, low level control, they're just non negotiable. And they actually tried to use Rust for several pretty serious projects.
So that gives us a really balanced, kind of high stakes perspective on the actual trade offs involved.
It's the reality check Rust kind of needs, maybe. Uh, so we'll start by acknowledging the strengths, the technical side that makes Rust so popular. Then we'll pivot. We'll look at that steep learning cliff, like 8 weeks steep, even for this experienced programmer. And finally, we'll try to synthesize their findings, figure out where Rust really shines, where it's worth it, and where, frankly, they decided to stick with other tools.
Okay, let's kick off this deep dive. Section 1, the undeniable strengths. The basic promise of Rust sounds almost revolutionary, doesn't it? Performance like C++ and maybe even better sometimes, but with memory safety guaranteed by the compiler.
And it's how they do it that's elegant. The sources really highlight these zero-cost abstractions.
Zero cost. What does that mean exactly?
Well, unlike C++A, where adding complex features often means, extra runtime overhead. In Rust, these features, when they're optimized properly, they basically disappear into the machine code. No extra cost at runtime. But the really critical part for performance, no garbage collection.
Okay, explain that. Why is avoiding garbage collection GC such a big deal here?
Well, think about languages like Java or maybe Go. They use GC, right? It handles memory automatically, which sounds convenient.
Yeah, sounds easier.
It is, but it introduces this possibility of a GC pause. That's when your whole program just stops briefly while the system cleans up memory. Now, if you're building high performance systems or latency sensitive servers or embedded stuff, those pauses, they can be disastrous.
Okay. Unpredictable delays.
Exactly. Rust enforces memory safety at compile time. So no GC pauses. You get predictable low latency performance.
That compile time guarantee. That's the dream scenario.
Right.
And a researcher noted it's not just theory. They were really impressed by what they called Rust's performance champions.
Oh, yeah, definitely. We're talking real world tools here that just blow away the older equivalents like Urge grep for searching text. Famously faster than grep.
Right, I've heard of that one.
And FAD for finding files, the Tashazide code editor, even parts of the fish shell. These things show Rust delivers real speed improvements where it counts system tools that often bottlenecks elsewhere.
And it's not just the language itself, the syntax. It's the whole ecosystem.
Yeah.
Right? We have to talk about Cargo, Rust's package manager. People call it the gold standard.
It really is. And it's the philosophy behind it. It's more than just pulling down dependencies like, NPM or pip. Cargo gives you this unified workflow for everything. Dependency resolution, sure, and it's reliable, but also built-in testing, documentation generation, even simplified cross-compilation, which can be a nightmare in C++. Plus great support for monorepos with workspaces. It standardizes the whole dev process.
Okay, so blazing speed, top-tier memory safety, amazing tooling. It sounds like a perfect package.
Yeah.
But we know there's always a catch in engineering. So what's the trade-off? What's the cost for all that safety and slick tooling?
The cost is conceptual overhead. Which brings us nicely to section 2, the ascent, that steep learning curve. Our researcher pointed out the barrier isn't really the syntax. It's 5 key concepts, all interwoven, that you have to get your head around before you can really be productive.
Okay, let's unpack those 5 hurdles.
Yeah.
Because this sounds like where a lot of people might hit a wall.
Yeah, it is. The list is ownership and borrowing, lifetimes, with the little A syntax, traits and generics, macros, and then the concurrency model. What makes it tough is they force this fundamental shift in how you think about code. It's not like going from Python to TypeScript, which is mostly syntax.
Okay, focus on ownership and borrowing for a sec. That's the big one, right?
Yeah.
How is it so different from what our C++ veteran was used to?
Right. So in C++s, you're managing memory yourself, right? Maybe using smart pointers or manual allocation deallocation.
Yeah, malloc, free, all that fun.
Or in garbage collected languages, the runtime just hides it all. Rust does something else entirely. It enforces automated resource management through a strict set of rules. Ownership means every piece of data has one and only one owner. Borrowing lets you give out temporary restricted access to that data.
So it's not manual, not fully automated cleanup like GC, but automated rule enforcement by the compiler.
Precisely. And that leads straight into the most notorious part lifetimes. What are they actually doing?
Yeah, that the thing looks intimidating.
So, if ownership is about who has the data, lifetimes are about how long that data is valid
Whoa.
and making sure any reference, any borrow doesn't outlive the data it points to. Think of it like a reference gets a time budget. The compiler makes you explicitly state, using that angle bracket thing, A, that the borrower won't hang on to the reference after its time is up. For programmers used to the compiler just figuring things out or dealing with dangling pointers later, this constant need to think about time, about the lifespan of data, it's a huge mental shift.
Okay, that definitely explains the learning timeline difference. Our researcher said, with Python or Go, you're usually productive in a week or two. How did Rust stack up for someone with their C++ background?
It was a marathon, definitely not a sprint. Weeks 1 and 2, just getting the basic syntax down. Weeks 3 and 4 were spent just wrestling with ownership and borrowing, constantly fighting the compiler. But the real hump, the big investment, was weeks 5 through 8. That's when they had to really grapple with lifetimes and the trait system. They noted that advanced stuff only started to feel comfortable after month 3. So you're basically sacrificing 2, maybe 3 months of immediate productivity just to learn how to build safely.
Wow, that's a significant upfront cost. During that intense 8-week period where the compiler was just saying no all the time,
Yeah.
did they mention feeling tempted to just, go back to C++?
Oh, absolutely. The notes definitely show moments of real frustration, deep frustration. I think the main thing keeping them going was seeing the potential benefit, that theoretical drop in runtime bugs. But yeah, that initial productivity hit, it's a major hurdle, emotionally and professionally. Rust really demands faith that the long-term payoff will be worth it, which, is a big ask if you're on a tight deadline.
That friction, that struggle.
Mm.
It brings us to section 3, the technical pain points. Let's talk about the borrow checker, the infamous gatekeeper. It sounds like it creates this painful loop in development.
Yeah, it's the core tension, isn't it? The researcher described this cycle. Write code dash compile fails, fight the borrow checker, sprinkle in some lifetimes, rework the code structure, try again. And it feels really inefficient sometimes because the checker often seems too restrictive or not always smart enough to see that a pattern is actually safe, even if it breaks a general rule.
Can you give a specific example? Something that really caused this C++ vet pain?
Sure. Take a simple vector like a dynamic array. Let's say you're looping through it, holding a reference to an element. Now, inside that loop, you try to push a new element onto the same vector. Compiler says, nope, instant failure.
Why? What's the danger?
Because pushing might make the vector reallocate its memory. It might need more space, so it moves everything somewhere else. If that happens, the reference you were holding, it's now pointing to invalid memory. Boom, memory corruption. So even if you know it probably won't reallocate in this specific case, the borrow checker enforces the strict rule. No changing the vector while you're holding on to a reference inside it.
Wow. Okay, that's a level of strictness you just don't see enforced automatically in C++R. But let's flip that. Given their background in C++R, which could be prone to subtle bugs, did they ever feel the borrow checker actually saved them? Prevented a bug they might have spent days chasing down later?
That's the crucial flip side, yes. The sources definitely mention this. Once they finally got a tricky piece of code to compile, they had this incredibly high confidence that it was memory safe. The compiler forces you to get the logic perfect up front. It prevents those classic C++ nightmares, use after free, data races, inconcurrent code. So yeah, the development time shifts. More time fighting the compiler.
Less time debugging runtime crashes.
Exactly. It's a trade-off. Pain now for reliability later.
Okay, moving on from borrowing. Let's talk about the trait system. Often praised as super powerful, but you mentioned it gets complex fast.
It is exceptionally powerful. It's how Rust does generic programming, handles polymorphism, deciding function calls at compile time or runtime, and allows for amazing code reuse. But unlike, say, simpler interfaces in Java or Go, when you start using advanced features like associated types, that type associated type thing inside a trait, And then you stack up complex, where clauses to specify capabilities, the code can become visually really dense, almost like hieroglyphics.
So those long trait bounds, like where tclone plus debug plus some custom thing item, suddenly the function signature is like 5 lines long.
Precisely, yeah. Reading complex REST signatures feels like mentally untangling this web of constraints. It definitely impacts readability, especially when you're starting out.
And this ties into a very modern problem: AI assistance. If I'm stuck on complex traits or lifetime errors, my first instinct now is, paste it into ChatGPT or Copilot. But our researcher found that wasn't always helpful.
Yeah, that's a current, very practical reality check for Rust. AI tools.
Mhm.
They still struggle quite a bit with the kind of localized, deep context needed for these complex ownership and lifetime puzzles. They often suggest patterns that are just wrong. Like they'll suggest returning a reference that the compiler immediately flags as dangerous.
Oh, interesting.
Or they might suggest really heavyweight solutions like wrapping everything in Arc or Mutex when just restructuring the code a bit would fix it. The fundamental rules of the borrow checker. They seem too nuanced for current AI models to really get right consistently. It basically confirms that you still have to master the concepts. You can't just delegate ownership thinking to the AI. Not yet, anyway.
Okay, so we've got this powerful language, but with real conceptual friction. Let's get practical. Section 4, the right tool for the job. Where did Rust get the green light? Where is it worth that upfront cost?
The cost makes sense where safety and performance are absolutely critical. The sources highlighted 4 main areas: safety critical systems, a performance sensitive infrastructure, embedded development, and anywhere C or C traditionally dominated.
Why embedded? Why did that stand out so positively in the notes?
Because it's kind of the perfect storm of requirements. Embedded systems, they often
Yeah.
run on hardware with very limited resources.
Right, tiny microcontrollers, things like that.
Exactly. They can't afford a big runtime environment, definitely can't afford a garbage collector pausing things. Rust gives you that low level control like C, the compiled efficiency, and modern tooling, without the constant risk of memory safety bugs. It essentially prevents entire classes of CC++ errors in places where bugs are incredibly hard to find and fix.
And we're seeing it move into really high stakes areas now, right?
Yeah.
Like the Linux kernel adoption. That seems significant.
It is, yeah. Rust is being carefully woven into the kernel alongside C, specifically using it for new components, new drivers, where they want that memory safety guarantee. The sources mention examples like Android kernel drivers, some Microsoft hypervisor parts, even new file system implementations using Rust. It's a pragmatic approach. Use Rust where safety is paramount, stick with C for the vast amount of legacy code.
Okay, so that's the green light. Conversely, where did this veteran dev say, hang on, yellow red light here, I'm reaching for something else?
Mostly it came down to iteration speed. How quickly can you try ideas out? So, for rapid prototyping, for just experimenting with algorithms, or even game development where the engine might already be C++ up, they lean towards Python or TypeScript. The constant back and forth with the borrow checker just slows down that initial creative phase too much.
Makes sense. What about web services?
For web services, APIs, things like that, go off and one out. Its concurrency model is simpler, and the compile times are incredibly fast. You get quicker feedback. And for data science, well, Python's ecosystem is just still untouchable there.
So it really sounds like Rust is the tool you pick when the final product absolutely must not fail, rather than the tool for when you need to iterate and explore quickly.
That sums it up pretty well, I think. And one last point they made was about the community. While generally super helpful and technically brilliant, the researcher did note they can sometimes be, let's say, overly enthusiastic about using Rust for everything.
The rewrite it in Rust meme.
Kind of, yeah. And that enthusiasm, while well intentioned, can sometimes pressure newcomers into using Rust for problems where, Go or Python might give you 90% of the solution in 10% of the time.
Okay, let's wrap this up and bring it back to you, the listener. Key takeaways. The final verdict from this experienced source seems pretty clear. Rust's technical chops, performance, safety, undeniable.
Yes, absolutely top tier. But that technical guarantee comes with a serious conceptual price tag. You have to master ownership, lifetimes, the trait system's complexity. So it's an amazing choice for those specific high stakes areas. Systems programming, kernel development, embedded. But if your main priority is speed of development, getting something working quickly, it's often overkill.
Which leaves us with that final provocative thought, straight from the researcher's notes, and it's something every team needs to consider. The best language is the one that gets the job done effectively.
So that really puts a strategic question back on you as you think about your next project. How do you actually weigh that trade off, the cost of development speed versus those technical guarantees? How many potential memory bugs are you willing to risk, maybe, to avoid that potentially painful, 8-week learning curve?